Hello, welcome to my Lab 3, where we look at a video of a slinky oscillating. In this lab, the purpose of this lab is to predict the motion of a falling slinky and analyze its effects of its surroundings. We will use Tracker, which is a software to track the observed position of the slinky at each time frame, GlowScript to create a computational model to predict the graph and ideal motion. The goal of this lab is to determine whether the bottom of the slinky stays stationary in the model. The result: although there are some fluctuations at the bottom of the slinky will remain stationary. Some of the fundamentals. The variables and system. The system of this lab is our slinky. The surroundings, everything else. The variables are the initial position, final position, average velocity, drag, and the net force. Some key assumptions that we can make while doing this experiment is that we can assume that the motion of the slinky is only in 2 dimensions, which is the x and y direction, and we can assume that the object behaves as a point mass. Some of the physics ideas which we will use is Newton's second law, which is the change of momentum divided by the change of time is equal to the net force, where momentum is equal to mass times velocity. From there, we can get the position update formula and the velocity update formula. With that being, the position update is the final position is equal to the initial position plus the average velocity times the change of time, with the velocity update formula being the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. The forces also that we can have is the force of gravity, which is negative mg, or g is 9.81 meters per second squared. The force of drag, which is negative bv squared, and the net force, which is force of gravity plus the force of drag. The variables that we will be using with the computational model that will stay constant the entire time is the mass, which is 0.218 kilograms, the height, which is 1.75 meters, the initial position, which is negative 1.632 times 10 to the negative fifth in the x direction, and 2.725 times 10 to the fourth in the y direction, and the initial velocity being 0. Some additional information we have about the tracker is that we first established an x and y coordinate plane that was in line with in parallel with the floor where the slinky was going towards. We set a calibration stick in meters in the x direction and in the y direction. We tracked the center of mass for each time frame of 0.033 seconds, and we saved the x and y coordinates to a spreadsheet. Here's some of the code where you can see I put in the mass of the ball, the gravitational force, the position and velocity initially. You can see that our time frame reached up to 5.5333, so we did a while loop where we calculated the net force and applied the momentum principle using the update object's velocity, and yeah. Here is the results of the bottom of the slinky predicted versus observed. You can see they're pretty much on the dot, with the observed being just slightly under with most of the slots. Some possible errors that I could have run into during this experiment was that the observed motion of the slinky could have experienced fluctuations due to the external forces which were not accounted for in the model. And another source of error could be from the inaccurate placement of the center of mass when tracking. Does the bottom of your model slinky stay stationary just like the video? The forces in the y direction cancel out. Although the gravitational force acts downward, the slinky acts as a big spring and counteracts the force with a tension force of equal and opposite magnitude. As long as we have a slinky that is either long enough or has a large enough spring constant so that tension equals gravitational, the weight will remain stationary until the top of the spring reaches it. And here is a link to my code.